It has to do with the Pertner hypothesis of OCCLT, and he and his fellow researchers established, I think it's about 2004, I think it's the first paper. They hypothesized that the main reason for finding thermal limits or thermal tolerance was the demand of oxygen at the level of the cell. So actually that poster and what Alessia has been talking to us is very, very important for this, for these kind of hypotheses and tests of hypotheses. So what he says is that there is a demand of oxygen at the cell, and that demand is the one that triggers a series of physiological, biochemical, and behavioral responses in the animals that will try in the first attempt to get more oxygen into the cell as quickly as possible. But of course, oxygen is very, very toxic. So as soon as it arrives in the cell, it starts to reduce everything. No? So there is an imbalance in the stress, oxidative stress, and there are a lot of reactive species, oxygen species, that very quickly start to finish with the cell. First with the membranes, lipoprotein membranes, and then with the rest of enzymes and all sorts of very, very serious damaging. And this damage ends with cellular apoptosis, and that's the end first of the cell, then of the tissue, and eventually of the animal. So what we wanted to look at is the possibility of some kind of cross-tolerance, because normally where there is very low oxygen, it is also accompanied by high temperature, and vice versa. So we thought that in the very, very shallow lagoons where this species is found, especially in Mexico and in the southern part of the Gulf of Mexico, you normally find very low oxygen levels, or at least very strongly fluctuating oxygen levels. And we thought that it would be interesting to see if there was some kind of cross-tolerance, so if there was some evidence of these animals being able to have a slight advantage of low oxygen availability associated with high temperature, as it has been found for other species, but it has not been generalized. In any case. So what we did was a very large experiment where we exposed animals to 3 temperatures, 26, 30, and 33. Similar to a 5-day, ours was 7-day exposure, constant temperature exposure. And at the end of that, we put them into respiratory chambers, and in the respiratory chambers, we decreased oxygen levels in 3. One is normoxia, 100%, then 60%, and then 35%. So very strong and severe hypoxia and moderate hypoxia. Only 24 hours, and at the end of that we measured all sorts of different things. We measured ICA, ICA is in Spanish, and in English it is apparent heat increment. We measured PAT, which is temperature-induced aerobic scope. We measured assimilation efficiency. We measured I have it over here. It is the anti-defense oxidation system. So a series of enzymes and other lipoperoxidation and carbonylative proteins. I mean, some biochemical indicators of how these animals are responding. And we found that, yes, they do have a very, very, very short and very short-lived window of opportunity in which they actually they are able of getting a little bit more energy, and probably in that very short window they would be capable of escaping, and we would be very interested in knowing if in that very short window they would be able to escape and move, and how far they could move. but that is very short-lived. So at the end of the day, although they do present this plus pejus is we have classified in optimum state, pejus state, which means like a little worse in Latin, no? Pejus, and this is a classification used by Perner and his people. And then we have identified a pejus plus. We've called it pejus plus, trying to refer to a small window in which they might be able to have a little bit of a surplus, and then a very quickly pessimum stage. Yeah? And with this classification, we have managed to try to unveil a series of mechanisms, basically biochemical and physiological mechanisms that could be explaining what happens to their energy reserves and what they do with proteins and what they do with carbohydrates and what is happening in their liver and what is happening in their muscle. So the next step is to see how mitochondrial respirometry works within both the hepatic tissue, liver tissue, and as well in the gills. And we want to look at immunological indicators at the kidney. Thank you. At the kidney. So that would be the next step. We will be doing that in the future. So, yeah, that's it.
Thank you very much, Maite.